Hey everyone, this is Mohammed Nadeem and welcome to my YouTube channel. Today in this lecture, we will know that how the force exert on a current carrying wire when we place that wire in an external magnetic field. So here in this diagram, we have the horseshoe magnet, and this horseshoe magnet will produce the magnetic field, and inside the magnetic field of this horseshoe magnet, we put the conductor, and we connect that conductor with the battery. So when the current is flowing through the conductor, the magnetic field will produce around this conductor. So that internal magnetic field of the conductor will interact with the external magnet, and due to which the force will exert inside on this conductor. So in this video, we will discuss this in more detail. So here we have the conductor, and that conductor is connected to the battery, and when the current is passing through this conductor, the magnetic field will produce around this conductor, and that magnetic field of the conductor, we call them an internal magnetic field. So the internal magnetic field of the conductor will interact with the external magnetic field of this horseshoe magnet, due to which some force will exert on this conductor, and due to which this conductor is rotating inside the magnetic field of the external magnet. So here we have the magnetic field of this external magnet, and inside the magnetic field of this external magnet, this conductor is present. So this conductor is also connected with the battery. So there will be some magnetic field will produce around this conductor. The direction of the magnetic field of this conductor is given by the right hand rule. The magnetic field around this conductor, and this magnetic field will have some north and south pole, and that north and south pole will interact with the external poles of the magnet, due to which the force will exert on this conductor, and this conductor will be moving due to that force in this external magnetic field. The direction of external magnetic field here is in this direction. So this is the direction of so here this is the direction of magnetic field, and the direction of the electronic current here is in the x-axis. So this is the direction of the electronic current, and which is represented by the black colored arrow here. So I'm going to pause this. Here, this black color arrow represents the direction of electronic current. So the electronic current is from the negative toward the positive. So this is the direction of the electronic current, and similarly, we have the force exert on this conductor, which is represented by this green colored arrow, and that is perpendicular to the magnetic field. So here the magnetic field is in this direction, okay, and this is away from our screen. So the magnetic field of external magnet and this force is perpendicular to each other, and similarly this is the direction of electronic current, and this is the direction of force exert on this conductor. So they are also perpendicular to each other. So the force exert on this conductor is perpendicular to the external magnetic field, and also to the direction of the current. So here we have, this is the direction of the current. Okay, this is the direction of the current, and now the direction of the force is perpendicular to the direction of magnetic field and also to the direction of the current. So this will be in this direction. So this is the force on the conductor. Force on conductor due to interaction of the magnetic field of the conductor with the external magnetic field. So here we can say that this is the x-axis, this is the y-axis. So in the y-axis, the magnetic field is acting, and the x-axis, the current is flowing, and on the z direction and the z-axis, the force and the conductor is present. So therefore, in order to determine the direction of the force and the conductor, we using the Fleming left hand rule for the electronic current. So in this Fleming left hand rule, we have this thumb, and the thumb represent the direction of the force exert on the conductor. The forefinger represent the direction of the magnetic field, and this middle finger represent the direction of the uh, current. So it represents the direction of electronic current. As here, these three fingers are perpendicular to each other, and similarly, these three, the magnetic field, the current, and the force, also perpendicular to each other. We will place our middle finger in this direction, and we will place the forefinger in the direction of external magnetic field. So here it will give the direction of this force. So here it will give the direction of this force which is outside from the screen. So here in this part of the conductor, the force is inward to the screen. Okay, and in this part of the conductor, the force is outside from the screen. Therefore, the couple will be produced, and due to this opposite direction of the forces, this conductor will be rotating inside the external magnetic field. Okay, this is the physics behind this. So due to that process, the current is moving in this direction, and the force will exert on this side and inward to the screen, due to which this side will be go inward to the screen. Okay, this side is moving inward to the screen, and similarly the force in this side is moving away from the screen. So therefore, the force in this on this side is inward to the screen, and the force on this side is away from the screen. So therefore, the this conductor is rotating inside this magnet. So here, if we take the screenshot from that, on this side, the direction of the current is this. So here we have the direction of the current, the electronic current, and this is the direction of the external magnetic field. If we put our the forefinger, the forefinger of our hand in the direction of this external magnetic field, and the middle finger in the direction of this electronic current, okay, of this electronic current, and the thumb will represent as the force exert on this part of the conductor. So here your thumb will represent the force inward to the screen in this side. So here in this side, the force will be exert inward. Okay, inward, inward to the screen. Okay, inward to the screen. And similarly, when the current is flowing in this direction, so here put your middle finger in this direction of the conductor, and the external put your forefinger with the direction of external field, and your finger will be pointing away from the screen here. So the force on this side will be away from the screen, away from screen. So here in this side of the conductor, the force is acting inward to the screen, and here the force is outward from the screen. So due to this, a couple will produce. Okay, so this side will be moved inward to the screen, and this is outward from the screen, and due to which this conductor will rotate inside the external magnetic field. Okay, and the force on this uh, conductor is due to the interaction of the magnetic field produced from this conductor with the external magnetic field. This is about the force, and that force is actually the vector quantity, and the vector quantity will have the direction. So here the direction of the force is inward, and here the direction of the force is outward, and due to which this conductor will rotate inside the external magnetic field. And this phenomena is mostly occur in the DC motor, which convert the electrical energy into mechanical energy. So here the force will exert on this conductor, and this force is vector quantity. So here this force is vector quantity. Okay, quantity. So it will have the magnitude. Okay, it will have the magnitude, and also it will have direction. The The direction of this force is given by Fleming left hand, Fleming left hand, left hand rule. Okay, and also it is given by the Fleming right hand rule. Okay, Fleming right hand rule and Fleming left hand rule. The Fleming left hand rule is used for the electronic current, is used for the force on the conductor in which the current is electronic. The direction of the current is from the negative side of the battery to the positive side of the battery. So for the electronic current, we will use this Fleming left hand rule, and for the uh, conventional current, when the current in this conductor is conventional current, then in order to find the force on this conductor, we will use the Fleming right hand rule. Okay, this was about the direction of the force exert on this conductor. Now the magnitude of the force is determined by some external factors. The magnitude of this force is depend upon the external magnetic field. If we increase the strength of external magnetic field, then more force will be exerted on this conductor. So here we conclude that the F is directly proportional to the external magnetic field, and the magnetic field is represented by B. If we increase the current from the battery, the force will exert on this conductor will more, because when more current is passing through this conductor, it will produce its magnetic field more. So due to its more magnetic field of the conductor, the interaction between this magnetic field of the conductor and due to the magnetic field of the external magnet will be increased. So therefore the force on the conductor will be increased. So here the force is directly proportional to the current in the conductor. Okay, and similarly the force is also increased when the length which is present inside the external magnetic field has increased. So F is also directly proportional to the length. So if we combine all these equations. So here it means that F is directly proportional to I, L, and B. Okay, these are directly proportional to I, L, B. So from here we can write that if instead of this proportionality sign, we will write if em is equal to sign and constant. Okay, constant here. So this is the constant, and instead of this proportionality, we write equal and constant, and this I L B comes in its own position. So here, if is equal to constant K I L B, okay, and here if the value of the K become 1, then this F will be equal to I L B. So this is the magnitude of the force which exert on the conductor present in the external magnetic field. So this is uh, the magnitude of that force. Okay, and the direction, we can write this force in the direction form as so. Here we have the direction of this force, which is given by F is equal to I L B sine of theta. I L B sine theta. So here instead of sine theta, we can write the cross, and here it will become equal to I L cross B. I L cross B. So we can apply this equation of the force on this diagram. So here I'm going to copy this diagram. So here I copy this and move this to here. Okay, this is our same diagram. So now we are going to apply this equation on this diagram. So here we have three cases. The angle between this L, the length of the conductor, and B, the external magnetic field, will be 90, because here the external magnetic field is in this direction from this north to south, and the length of the conductor is this. So here will be angle 90. So for this, F is equal to I L B and sine 90. Okay, and sine 90 is equal to 1. So it become equal to I L B. So this was the first case. And for the second case, when for this part of the uh, conductor. So here for this part of the conductor, the external magnetic field. So the external magnetic field is in this direction. Okay, from the north to south here, and the length of the conductor is also in this direction. Okay, this is the B and this is the L. Okay, and here from the theta, in this case theta will be equal to 0. So put 0 instead of this theta, we will put the 0 here. So this become F is equal to I, okay, L B, okay, and sine of 0. And sine 0 is equal to 0, and 0 will multiply to all these factors, and it will give us the force. And this part of the conductor is 0.